Hi, so my name is Renata Wiśniewska and I am working at the Leibniz Institute for Astrophysics in Potsdam. And today I would like to give you some very short overview about the high-resolution ground-based observations and space mission and how to plan and coordinate the campaigns. So coordinated observations with ground-based and space-borne telescopes. The main idea of this is that we supporting the ground-based data by the satellite mission, because high temporal and spatial and spectral resolution data from the ground-based telescope has a short time series and they are mostly very affected by the seeing. And observations from the space-borne telescopes has a long data series, lower spatial resolution, and are not affected by seeing. They are also mostly available online, so this is like a big advantage to kind of link them together. But the question is how to do it. So we have multiple telescopes and how to join the observations and what instruments are available currently. So for the most solar telescopes, the observing time is allocated based on proposals. And these proposals specify a scientific goal and setup of chosen instrument and require time range for the observations. And one idea is to submit the SolarNet project or SolarNet program for the joint observations. And usually in this case, call for observing proposals are announced once or twice a year at the website of the telescope at the host institution, or that you can find them easily on the website of SolarNet. Okay, so if you go to the SolarNet project.eu, you can find, for instance, program call for proposal, let's say for the ground-based telescopes like Gregor, SST, and THEMIS. It is also possible for the other instruments, and you can easily coordinate them also with the space-borne telescopes. So as a space mission, we have, so one choice can be like, for instance, Solar Dynamics Observatory, and these have different instruments on board, and with the Solar Dynamics Observatory you can observe either with atmospheric imaging assembly, AIA, or the helioseismic and magnetic imager, or both. So you know that these data are available like all the time, 24/7, in several spectral ranges. So you have different prefilters, different time cadence, and you can observe basically the lower chromosphere, upper chromosphere, corona, and also some continuum data. You can also have the line of sight photospheric magnetogram with a cadence of about 12 minutes. So, but I suppose that every one of you knows it. Then we have a possibility to observe with IRIS. So IRIS have 2 seconds temporal resolution and 0.3 to 0.4 spatial resolution, and also several passbands. Then the next one is HINODE. HINODE has 15, has for instance ICE instrument, which is UV imaging spectrometer, and takes spectra in 15 spectral lines. So you have like really a lot of possibilities to coordinate your observations with all of these 3 space missions. And lately we have also Solar Orbiter, which has a lot of instruments from the EUV through photospheric and magnetic data, and also some X-ray measurements. So this is like really a lot, but since I don't have time to go into the details with that, I will show you only the ground-based telescopes, and I will just go with like very quick through it. So as a ground-based, we have also some multiple choice here. So we have Gregor, and the first 3 are located at the Teide Observatory. So we have Gregor, THEMIS, and VTT. So both three of those telescopes are located in Teide, but they are like like ownership of different countries, and have also multiple instruments to choose. You have to like really, if you want, you have to go through the website of these several telescopes, and you can check the instruments which are there. I will be talking today about the Gregor like more specifically, and you can see that all of these telescopes has a different apertures, but the biggest one in Europe is for now the Gregor telescope. In US we have GST, and of course DECIST, which is a very new one, and to be honest, I didn't solve any results from this so far, so we are still waiting for it. And if you want to observe or coordinate observations with China Observatory, then we have NVST, which has also very good facilities. Okay, so but as a ground-based telescopes, most of them are in an optical range, so optical telescope in infrared and visible range. We cannot observe UV with ground-based, unfortunately, because of the of Earth's atmosphere. And additional to that, we can coordinate our observations with some infrared, radio interferometers, which is LOFAR and ALMA. And you can also write a proposal to use these specific instruments to observe or to address your scientific goals. And as we did like some kind of report on the coordinated observations which were organized so far, and we know that that mostly people are observing with Gregor telescope so far, so this is like 65% are using and applying for observation with this telescope. And the second on this list is SST, then VTT, and then you have the rest. And as you can see, the most interesting topic or the measurements are the spectroscopy and polarimetry. Imaging is also like 56% of interest. So you can see how much popular are these instruments now. And what I have to mention that with Gregor, you can take both spectroscopic and polarimetric measurements at once. So yeah. So what is the Gregor? So Gregor is a 1.5 meter solar telescope and the largest European solar telescope for the visible and near-infrared spectral regime. So it was designed to measuring the photospheric and chromospheric magnetic and velocity fields with a very high spatial and temporal resolution. And it, of course, uses adaptive optics. So adaptive optics correct the wavefront of the atmospheric turbulence. So we still have some shaking at the image, but this is kind of corrected and it looks much better when the telescope, now all of them are equipped with the AO system. So it is possible to observe with a multi-measurement, multiple instruments simultaneously at Gregor, and basically these are the three available instruments. So first is the Gregor infrared spectrograph. So here you get the spectropolarimetric measurements, then is broadband imager and high-resolution fast imager, HiFi. Okay, so the BBI has two independent wavelengths channel, and this is G-band and TIO filters. However, any two different interference filters can be used depending on the science, on your science case that you apply. The field of view is about 60 by 50 arc seconds, and the image scale is 0.02 pixel per pixel, arc second per pixel. And the system is currently being also upgraded. So we do some upgrade at this telescope to include the further imaging channels using a layout filter for observing and strong chromospheric absorption in calcium 2K line and H alpha. Then we can use Gregor infrared spectrograph. So you obtain all of the 4 polarimetric states, so stocks E, Q, U, and V. And it can be carried out either as a slit or an integral field unit, so this IFU. And then we can observe in 2 wavelength ranges, and the first is the one up to 1.3 microns, and the second one is 1.5 to 1.8. Yeah, so then we have some parameters. What can we study? Waves and oscillations are the prime candidates for the 3D spectropolarimetry in the IFU mode, and it has also a relatively small field of view. It's only 6 by 3 arc seconds, but the larger field of view is also possible if several observed patches are stitched together in a mosaic. So this is what was shown also in Mikhail talk. I don't remember the name correctly. Okay, so with the HiFi, so we have improved now the high resolution fast imager, and now we have 6 lines which are possible for measure. And first camera, which called HiFi Plus 1, measures at the G band and 430 nanometers, and the blue continuum and 450. The field of view of this camera is 70 by 60 arc seconds, and it's possible to measure with 12 seconds cadence. So if you have such a measurement, then we do like a kind of image selection. So we take out best 100 images out of 500 which was taken at the measurements, and then we do spectral masking and image restoration of the multiple object multi-frame blind deconvolution. So this is this MOMF-BD. Then the second narrow band is the H-alpha filters, and this is a narrow band and the broadband window for H-alpha, and this has a very similar field of view, so also 76 by 60 arc seconds at this time, and the temporal cadence is 6 seconds in the case of this camera. And the HiFi Plus 3, we have 2 lines, and this is calcium 2H and a telluride line, so TIO. And the field of view is the same as the HiFi Plus 2. And for all of these lines, you have already at the telescope, so the data processing pipeline. So basically, you will end up with processed data. So as your measurement is done, so you finished your measurements, so you can immediately do the correction and reduction of the data. So, and the idea actually for the joint observation in general is like to have space data and then look precisely to some very, very small area where your magnification will be large enough to resolve very, very tiny features, like in case of this sunspot. Actually, this beamer is not so good, but you can see that the granulation is very nice resolved. But this is reduced and speckle reconstructed data already for this tiny sunspot. And the line of this measurement is telluric one. Oh, sorry. Yeah. So here I would like to show you also some other HiFi Plus data examples. So we have speckle restored data for different active regions, but this is all for the calcium line images. So different features can be resolved very well with this line after the reconstruction. Here you have the speckle reconstructed G-band images at 430 nanometers. So these are like slightly different. And here you can see the month BD restored data for 8 alpha narrowband images. So you can see all of this after the restoration. You can see like very, very tiny features here, which can be very nice resolved using ground-based observations. And actually, if you compare then this kind of data to, let's say, I don't know, SDO or IRIS or whatever instrument you want, you can gain the information not only from the photospheric level, from chromosphere, but then you can compare it to corona, which is very, very useful nowadays. And I highly encourage you to apply for the ground-based observations. It can be Gregor, it can be also one of the telescopes which I mentioned. So what are the best, as a summary, what are the best practices for coordinated observations? So the recent coordinated campaigns show us that the arrangement of more than one ground-based telescope is really, really challenging. And in many cases, the co-pointing with many telescopes is impossible. Please keep in mind that they are located at the different observatories. Therefore, the idea of following target for like a longer time by observatories around the globe is currently one of the potential solution of this issue. So basically, you starting to measure with one observatory, and then you just following, doing to the day with some other telescopes. This is possible, although it's not so easy to plan. So therefore, the observing campaigns should be planned like really, really well in advance. And good practice will be in that case to write a request to the institution hosting the telescope, or contact the person which is responsible for the instruments. And basically all of the information can be found at the pages of the institutions or observatories or telescopes. Then some solar telescopes can be operated also remotely. So you basically just write your proposal, and then you are just saying that you want to observe in a remote mode. And for some of them, this is the only way to observe, actually. So the guys which are responsible for taking observations will take the data for you, and you will just get the products already. So, or the access to your data, which were measured by someone else. Sometimes it's possible to go like in person to have an observation at some telescopes. But this is depending on the observatory, on the instrument, and so on. So, and also often the observations are carried out at different times. So to observe the same region on the solar disk, a common coordinate system and its transformation with the time must be considered. So basically, the calculation of the coordinates of the interested region needs to be done like sometime in advance to determine the accurate location of the observed region at the given time. So you need to just think about it, that if we observe with, let's say, the Keys on Hawaii and with, let's say, Gregor at Tenerife, these are like in a different locations. So also the time zone is not the same, and then also our coordinates of our observed region may be different for them. So you need to consider that. But the SolarNet metadata recommendations, which you can access easily, this is like published in 2020, provides the convenient framework to plan this solar measurements. And overall, such a coordinated campaigns can be really, really successful, and they are nowadays very popular among the scientists. So because they are joined involve a lot of institutions around the world and co-working of many scientists, and brings additional scientific benefits. So I really encourage you to think about some joint observations of ground-based instrument and then coordinated with some space-borne telescopes. because this might be like really, really beneficial for your scientific goals. Okay, so here are the references of some papers, and thank you very much. So if you have a question,